Right, let's go through this practical that we did today and make sure we all understand how to measure the mass of the ruler using the principle of moments. Right, so as I said in the video, it's quite straightforward. All you need is the meter ruler, the something to pivot on, which is what the triangular block is, some slotted masses. We've got 10 gram slotted masses and a small bit of string. It's as simple as that. So it's all about getting the ruler to balance. Now, before we get it to balance, we locate the center of mass. And we do that, it's going to be roughly in the middle. Okay, it's going to be roughly in the middle of the ruler. But we do that without the slotted masses. Now we can see that when I marked it, it was this position here, which was, if you remember, I think I said it incorrectly at the start of the video, that was at the position 503 millimeters on the ruler. So it's roughly near the center of the ruler. Okay, so this position here, this meter ruler position was 503. So that is in millimeters. That's the position of the center of mass of the ruler. Now that's the point from which all of the weight of the ruler is going to appear to act from. That's the definition of center of mass or center of gravity. Okay, obviously there is wood in the meter ruler either side of the pivot. Okay, but all of the weight of the individual bits of wood in the meter ruler are going to basically combine to produce a resultant overall weight, which acts from here, the center of mass. Okay, so that's the thing that's going to be producing the anti-clockwise moment in the diagram here. Right, now to balance it, okay, we need slotted masses on the other side. So we've got the slotted masses here. Okay, now as a result, we've had to move the pivot towards the right, sorry. Okay, so now the new position here is the new position of the pivot. Now, if you remember from the video, I kept the position of the slotted masses constant. I think that was 950, wasn't it? 950 millimeters. So this position here on the meter ruler was also kept constant. Now the thing I varied, the two variables here, I varied the weight of the slotted masses. Now I went for 20 grams, 40 grams, 60 grams, and as a consequence, the position of the center of mass changed as well. Okay, so as we can see here, with our new pivot position, we have the two forces. So we've got the weight of the ruler, okay, the weight of the ruler going down there, and the weight of the slotted masses going down there, each producing opposite moments where that's the pivot. Okay, right, how to do the calculations to find the weight of the ruler. Right, so like I said, these positions 503 and 950, I kept those constant. Obviously the center of mass is not going to change for the ruler, and I kept the slotted masses at 950. Right, now the results were this. If you play through the video, you should have got down these results. So for 20, 40 and 60, like I said, the center of mass position doesn't change. Okay, so the position on the ruler was 503 millimeters. The position of the slotted masses doesn't change. That was 950 millimeters. What does change, as you can see, is the pivot position. The heavier the mass, the more the pivot position moves towards the slotted masses. Hopefully you can see that. Right, now how to calculate D1 and D2. So we're after here D1 and D2. D1 is the position, is the perpendicular distance of the weight of the ruler from the pivot, and D2 is the perpendicular distance of the weight of the slotted masses from the pivot. Okay, so we need to calculate D1 and D2, which from our table here. Okay, D1 is the position of the center of mass from the pivot, so it's 585 minus 503. And D2 is the perpendicular distance of the slotted masses position from the pivot, so it's 950 minus 585. And that gives us these results here. Okay, so for the three different values of mass, we've got the three sets of values of D1 and D2. Okay, now it's just a case now of using the principle of moments. Now you can do this. I've asked you to do this 3 times and have 3 goes at finding the mass of the ruler. Should be the same. The mass of the ruler is not going to change. Right, so it's all about the anti-clockwise moment and the clockwise moment being equal. Now remember, there's only 2 forces on the ruler producing a turning effect. Forget about what's happening here. Forget about any force acting here, because that's the pivot. Any force acting at the pivot is going to have no turning effect because there's 0 distance from the pivot. The only 2 forces that are going to produce a turning effect is the weight of the ruler, producing an anti-clockwise moment, and the weight of the slotted masses, producing a clockwise moment. Now, those 2 moments, like I said, should be equal, as stated by the principle of moments. Right, weight of the ruler, weight of the meter ruler times D1 equals weight of the slotted masses times D2. Now, the weight of the ruler is, do you remember, the weight of the ruler is the mass of the ruler times 9.81. And that multiplied by D1 is equal to the anti-clockwise moment. Right, the weight of the slotted masses, okay, the weight of the slotted masses, ms, times 9.81 times D2. So that's the clockwise moment. Now, we measured our distances in millimeters. Well, that's fine because we've measured the distance in millimeters on both sides. Okay, so D1 and D2 are both in millimeters, so we can leave them in millimeters. We don't have to convert to meters. Now, we also measured the mass in grams, didn't we? We also measured the mass in grams. So to convert to kilograms, we'd have to divide by our mass, our value in grams by 1,000. Okay, so there you have it. Principal moments, anti-clockwise moment equals clockwise moment. Now this is this little shortcut. Because we have both sides being divided by 1,000 and both sides being multiplied by 9.81, we can get rid of that, can't we? And we can also get rid of that. So that actually makes it a lot more simple, doesn't it? So the mass of the ruler in grams times D1 is equal to the mass of the slotted masses in grams times D2. Simple. Right, let's check whether this works. So let's take the first one. So 20 grams for the slotted masses, 82 and 365. 82 and 365. So 82, 365. Mass of the slotted masses was 20 grams. So the mass of the ruler times 82 should equal 20 times 365. Calculator, let's check. Right, 20 times 365 equals, divided by 82 equals, this gives us the mass of the ruler to be 89.02 grams. Okay, I've given it to 2 decimal places because I use the top hand balance at the end of the video to measure the mass of the ruler exactly to 2 decimal places. Right. Hopefully that makes sense. Have a go with the other sets of values and see if you get the same value of mass. Right, it's been a pleasure explaining that. Thank you very much. Goodbye.